Hi, I'm Gautam and I will present our work Deep Burst Super Resolution. When we take an image, we obtain a sampled version of the scene, the resolution of which is limited by the imaging sensor. Single image super resolution approaches aim to improve the image resolution using learned image priors. While they can generate natural looking images, they fail to recover high frequency details from the scene due to lack of information. A burst, on the other hand, contains multiple images of the scene captured successively. Due to natural hand motion, each of these images provide a different sampling of the underlying scene. This raises the possibility of using information from these multiple images to generate a high resolution output. We tackle this burst super resolution problem in this work. Our model takes the raw burst as input. Each image in the burst is first passed through an encoder to obtain deep image embeddings. Next, we align each of the image embeddings to a common reference image in order to compensate for camera and object motion. The alignment is performed by computing pixel-wise displacement vectors between the reference image and the current image using an optical flow network. The aligned embeddings are then merged together using the fusion module and passed through the decoder to obtain the super resolved RGB image. Next, we describe our fusion module in more detail. Ideally, the fusion module should be able to merge an arbitrary number of input images. Furthermore, it must be robust to possible alignment errors due to inaccurate optical flow estimation. While simple pooling operations such as average pool or max pool can satisfy the first property, they lack the flexibility to tackle the latter issue. Thus, we employ an adaptive weighted sum-based fusion approach in this work. For each image, we first obtain element-wise fusion weights, which are multiplied with the image embeddings and then summed together to obtain the merged output. The fusion weights are predicted adaptively by the weight predictor module using three sources of information. Firstly, the reference image embeddings, which contains information about the local image structure. Secondly, the residual between the aligned embeddings and the reference embedding, which can indicate possible alignment errors. And finally, the subpixel sampling location of data. The fusion weights allows us to adaptively merge the input images to obtain good performance. In order to train and validate our approach on real-world bursts, we also introduce a dataset named Burst SR. Our dataset consists of raw images captured from a handheld camera. For each burst, we also capture a high-resolution ground truth using a DSLR with a zoom lens. We collect 200 burst sequences with diverse scenes, where each burst contains 14 raw images. Our model is first pre-trained on synthetically generated bursts. Next, we fine-tune it on the training split of our burst SR dataset using an L1 loss. Note that as the bursts and the HR images in our dataset are captured using different cameras, there exist spatial and color misalignments between the two. In order to handle this, we warp the network predictions to the HR ground truth and perform a color space transformation before computing our loss. Next, we briefly look at our results. All our experiments are performed for super resolution by a factor of 4. First, we investigate the impact of number of input images. We observe that the performance of our model improves consistently with increasing burst size. When using a burst with 14 images, our model outperforms a single image baseline by over 2.7 dB in PSNR. Next, we evaluate alternate fusion approaches, namely average pool, max pool, and concatenation. We observe that our adaptive weighted sum fusion provides the best results. We also conducted a user study on Burst SR test set to compare our method with other single-frame and multi-frame approaches. The users were asked to rank the predictions of all methods for each image crop. We obtained 5 independent rankings for each of the 300 crops. Our approach obtains the best mean rank. Furthermore, the output of our method was ranked as the best among all methods in over 53% of the times. Finally, here is a visual comparison with a single image baseline. We observe that our approach can better recover high frequency details by fusing information from multiple images. Thank you.